I welcome you back to the third part and the fourth part of this tutorial on 4 decades of array signal processing research and optimization relaxation perspective. My name is Marius Pesavento from TU Darmstadt, and I will guide you through the second half of this tutorial. In the second part of the tutorial, my colleague Minh Trinh-Hoang has introduced the partial relaxation technique, where he has relaxed the interference part of the n-dimensional manifold structure of the array with the objective to reduce the computational complexity associated with multi-source optimization methods. Now in the third part we will also consider partial manifold relaxation, however not in the form of interference structure relaxation but in the form of array geometry relaxation. I will revisit existing subspace estimation techniques and introduce them from a slightly different perspective than they were introduced in the literature, using the concept of manifold relaxation of multi-source optimization criteria. We will then also discuss sparse reconstruction-based or compressed sensing techniques as sparse optimization techniques that apply the concept of approximation and relaxation. So we will first consider the popular ESPRIT algorithm. ESPRIT stands for estimation of signal parameters via rotational invariance. And ESPRIT is applicable in the case of shift invariant arrays. So these are arrays composed of 2 identical subarrays displaced by a baseline delta. And the situation is displayed over here. So we have an overall array which is composed of 2 subarrays, the red and the blue subarray, where the red subarray has a corresponding steering matrix A underbar of theta, and the blue subarray has a corresponding steering matrix A overbar of theta. Now these 2 subarrays are identical and they are shifted by a known baseline delta. So as these 2 subarrays are identical, also their corresponding array manifolds are identical, and these are denoted by calligraphic AN sub. So AN sub is the manifold corresponding to each of the subarrays. We assume that the number of sources n is smaller or equal to the number of sensors in each subarray. If m is the number of sensors in the entire array, then m by 2 is the number of sensors in each subarray. The steering matrices of the 2 subarrays, that is A underbar and A overbar, both belong to the same manifold AN sub, and they only differ in the position of the reference sensors. Hence their relation can be expressed as given here. The steering matrix A overbar of the blue array is equal to the steering matrix A underbar of the red array if we multiply the latter from the right with the diagonal matrix A of theta. The diagonal matrix is implementing the effects of the array shift by baseline delta, and delta is a diagonal matrix containing the complex exponentials that implement the shift. That means these diagonal elements lie on the unit circle where the individual exponents depend on the baseline delta and the respective directions of rival theta 1 to theta n. The overall steering matrix A of theta can be partitioned into 2 parts, the red and the blue, corresponding to the steering matrix of the first subarray and the steering matrix of the second subarray, respectively. Inserting the relation between the 2 steering matrices, this block structure can also be expressed in terms of the steering matrix of the first subarray and the diagonal phase shifting matrix delta of theta. Similarly, we partition the signal subspace matrix US that we obtain from the true array covariance matrix. The first n by 2 rows correspond to the first subarray and form the matrix US underbar, while the latter m by 2 rows correspond to the second subarray and are denoted by US overbar. In this tutorial, we introduce the ESPRIT algorithm, more precisely the less well-known totally square ESPRIT, from an optimization relaxation perspective. Hence, we will introduce totally square ESPRIT in the context of a subspace matching technique with partial manifold relaxation. Towards this goal, recall that the steering matrix A of theta for the true source directions and the corresponding exact signal subspace matrix US obtained from the true covariance matrix both span the same subspace, that is the signal subspace. Thus there exists a non-singular matrix K such that A of theta multiplied with K from the right equals US. Thus for the finite sample estimate of the signal subspace matrix denoted by US hat, this property suggests the following subspace fitting criterion where we fit the product of A times K to the estimate of the signal subspace matrix US hat in a least square sense. We minimize this subspace fitting function with respect to the matrix K, which is an arbitrary complex matrix, and with respect to the steering matrix A, which belongs to a highly structured manifold denoted by calligraphic A sub n as defined by this set over here, where we observe the shift invariant block structure in the characterization of the steering matrix. We remark that the upper block represents the subspace steering matrix A underbar that belongs to the subarray manifold calligraphic A n sub, and D of theta is a diagonal matrix with roots on the unit circle. Due to the non-convexity of the array manifold, in particular the block structure with the subarray manifold structure and the diagonal shifting structure, the subspace fitting function is highly multimodal and an exhaustive multidimensional search is required in the minimization. To reduce the computational complexity, the idea of the totally square ESPRIT algorithm is to partially relax the manifold structure. Towards this end, we relax the original array manifold structure in the optimization and introduce a relaxed manifold structure denoted by calligraphic A sub n ESPRIT. This manifold is defined as a set of all n times n matrices composed of two blocks, where now the first block A underbar no longer belongs to a subarray manifold, but it is an arbitrary non-singular complex n by 2 times n matrix instead. Similarly, in the second block of the matrix D is also a diagonal matrix as in the original manifold, but the diagonal elements are no longer restricted to lie on the unit circle. In other words, D is an arbitrary diagonal matrix, now parameterized in the directions of rival theta as before, which are the parameters of interest, and in the radii R1 to Rn, which are of no particular interest. With this relaxation, the subspace fitting problem can then be reformulated as minimizing the subspace fitting function over the set of all n times n complex matrices K and over the set of steering matrices A that belong to the relaxed ESPRIT manifold. Now inserting the block structure of the signal subspace matrix US hat and employing the block structure of the relaxed steering matrix, we arrive at the second line where we minimize the matching function with respect to an arbitrary complex n by 2 times n matrix A underbar, an arbitrary complex n times n matrix K, and an arbitrary diagonal matrix D. To characterize the solution set of the relaxed problem, we introduce additional variables. We replace the product A underbar times K by the matrix US underbar breve, and we replace the product A underbar times D times K by US overbar breve. We can further eliminate in the two constraints the variable A underbar. We can resolve one of the equations with respect to A underbar and insert it into the second equation. Then we arrive at the following problem formulation. The resulting formulation no longer contains the matrix A underbar, but it only depends on the newly introduced variables US breve instead. The constraints can be further rewritten in form of a null space property as given in the second problem formulation on this slide. In this form, the constraint states that any feasible solution for the concatenated matrix US breve must lie in the null space of the matrix on the right side of the product, that is, the matrix K inverse times D times K stacked over the negative identity matrix. Now, as the matrix on the right side is of dimension 2n times n, the null space of the matrix is of dimension n. In other words, the null space property implies then that the concatenated matrix US breve exhibits a rank that does not exceed the dimension of the null space, and that dimension is equal to n. Hence, the inner optimization problem represents the well-known best rank n approximation of the n by 2 times 2n repartitioned finite sample signal subspace matrix US hat underbar concatenated with US hat overbar. To compute the best rank n approximation, we first define the singular value decomposition of the matrix repartitioning, and this is given by the sum of 2n outer products with singular values sigma k and left and right singular vectors gk and hk respectively. Assuming that the singular values are arranged in non-increasing order, the best rank n approximation is given by the sum of the principal n rank 1 components as given over here. With this, the solution for the inner optimization problem is given, and we can use the null space property to compute an estimate of a matrix psi hat, which defines the matrix product K inverse times D times K. This matrix product can be computed as a least squares solution provided over here. And as we are interested in the exponents on the diagonal elements in D, more specifically the arguments in the exponents, we can diagonalize matrix psi hat by computing the eigenvalues of psi. The total least square ESPRIT algorithm is thus carried out in the following step. First, we compute the eigendecomposition for the sample covariance matrix R hat to obtain the sample signal subspace matrix US hat, which we partition as US hat overbar and US hat underbar. Next, we compute the best rank n approximation using the singular value decomposition. Then we compute the matrix psi hat as a least square solution provided over here. And finally, we compute the eigenvalues of the matrix psi hat, and from their complex arguments, finally, the estimates of the directions of arrival. Recall that we started our derivation of the total least square ESPRIT algorithm from the subspace fitting formulation that matches the finite sample estimate of the signal subspace matrix to the model A times K. If we start from a slightly different subspace fitting formulation where we actually apply a weighting with the inverse of the matrix K, that is, we use the formulation in the second problem, then interestingly, we will arrive at the conventional least square ESPRIT algorithm. Finally, we remark that both least square and total least square ESPRIT are search-free, multi-source estimation techniques that are extremely simple in the implementation. Furthermore, as we relax the manifold structure of the subarray in the derivation, the knowledge of the subarray structure is not required in the computation of the ESPRIT estimates. Finally, we can also relax the requirement that the number of sources n does not exceed m over 2. For example, in uniform linear array geometries, as provided here, we can partition the array steering matrix into two overlapping subarrays where part of the sensors belong to the first and the second subarray at the same time. For example, we can define matrix A underbar as a subarray steering matrix containing the first m-2 sensors, and A overbar as a subarray steering matrix containing the last m-1 sensors. Closely related to the problem of DOA estimation in shift invariant arrays is the problem of DOA estimation in partly calibrated arrays. In the ESPRIT algorithm for shift invariant arrays, we have relaxed the subarray manifold structure. Hence, the subarrays in the ESPRIT algorithm can be arbitrary and unknown. In the following, we consider partly calibrated arrays composed of multiple subarrays where we assume each subarray to be perfectly calibrated, but we assume the inter-subarray displacements to be unknown. The situation is displayed in the figure over here, where we characterize the sensor positions by assuming that the phase references of each subarray lie in the first sensor. Then the sensor position of the M sensor in the P subarray can be computed by taking the position of the sensor in the subarray and in adding the displacement delta P to it. Here we consider a linear array for simplicity, but we are not restricted to linear arrays in our derivations. Let the array response of the P subarray be given by a vector AP of theta, as given over here, and the corresponding n-source array manifold of the P subarray be a set of MP times n dimensional steering matrices with steering vectors of the structure given above. The overall steering vector of the array can then be written as a concatenation of subarray steering vectors of all subarrays, where each subarray steering vector is multiplied with a phase rotation term to account for the displacement of the subarray, or if you want, the phase reference, the displacement of the phase reference sensor. This concatenation we can also express in terms of the matrix vector product of a block diagonal matrix that contains the subarray steering vectors on the block diagonal. This matrix we denote by T of theta, and a vector that accounts for the phase shifts due to the subarray displacements. This vector can be considered as a reference sensor steering vector, and it is denoted by h of theta, and it's also a function of the displacement delta. Vector delta contains the p-1 subarray displacement as defined over here, measured relative to the first subarray. Again, we define T of theta as a block diagonal matrix containing all subarray responses. This matrix only depends on the directions of one source, and it does not depend on the subarray displacements delta. The reference sensor steering vector is denoted by h of theta, and it also depends on the displacement vector delta. With this parameterization, we can factorize the steering vector of the overall array A of theta as T of theta times h of theta and delta. Correspondingly, we can define the overall n-source array manifold, denoted by calligraphic AN, as a set of all m times n steering matrices with columns that can be factorized by a block diagonal matrix T and a reference sensor steering vector H, where T and H themselves belong to manifolds calligraphic T1 and calligraphic H1 that is defined over here. We consider first the fully calibrated array with known subarray displacements delta. Then we can apply the spectral music estimator, which we have introduced as a single source approximation of the weighted subspace fitting criterion with identity weighting before. Recall that in music the DOAs are estimated as the n deepest minima of the music function given over here. Inserting the convenient factorization of our steering matrix and replacing the steering vector A by T times H yields the following equivalent representation of the music function. This function we minimize with respect to H and T and find the n deepest minima with H and T belonging to the manifolds calligraphic H1 and calligraphic T1 respectively. The problem that appears is that the subarray displacements in the partly calibrated array are unknown in practice. Therefore, the reference sensor steering vector H depends on both the displacements delta and the DOAs. A simple spectral search is therefore not possible, and a p-dimensional search is required instead. We search for the directions of arrival of a single source and additionally p-1 subarray displacement parameters. Furthermore, ambiguities may exist in the reference steering vector. Different displacements may yield the same steering vector. Yeah? However, we remark that the subarray response matrix T of theta is independent of the displacements, and that's a property that we can use in the following. The idea of the rank reduction short rare algorithm is to relax the structure of the reference steering vector h and to replace steering vector h of theta and delta that belongs to the manifold calligraphic h1 by an unstructured vector c in the complex space with the same norm being equal to p. However, we maintain the manifold structure of the subarray response matrix T of theta that does not depend on the subarray displacements delta. Hence, we introduce a relaxed or partially relaxed array manifold calligraphic AN over bar as a set of all steering matrices A with columns that can be factorized as a matrix T times an arbitrary vector C, where T belongs to the manifold calligraphic T1 and C is an arbitrary norm P complex vector. Inserting the relaxed steering vector into the optimization problem yields the modified function given here that we minimize over the relaxed manifold. So we minimize with respect to T and C. The advantage of the relaxation is that it separates the minimization with respect to C from the minimization with respect to T. In other words, we can first minimize with respect to C as an inner optimization problem and then find the n deepest minima with respect to the structured manifold matrix T. The inner optimization problem can be solved in closed form. The solution C star is given by the minor eigenvectors or the minor eigenvector of the matrix N as given here. That is an eigenvector corresponding to the smallest, the zero eigenvalue. Inserting this solution back into the objective, we obtain the rare criterion that only depends on the source DOA. So hence we can employ a spectral search to find the directions of arrival. The rare function is the smallest eigenvalue of the rare matrix M that we have defined. Instead of computing the smallest eigenvalues, we often use the determinant of the rare matrix, which also vanishes at the true source location in the asymptotic case of large signal-to-noise ratio or a large number of snapshots. Often computing the determinant is easier than computing the eigenvalues. The matrix M is of dimension P times P, so the number of subarrays. If P is larger than N, the number of sources, we can apply the Schur complement and use an equivalent reformulation with a rare matrix of dimension M times M, for which we can either compute the minor eigenvalue or also evaluate the minima of the determinant. Next, we turn our attention to the sparse reconstruction methods for direction of arrival estimation, and these methods became extremely popular in the past 15 to 20 years, not only in the context of array signal processing but also beyond. Sparse reconstruction methods, often also referred to as compressed sensing techniques, are based on our underlying model assumption that the number of sources in the field of view is comparably low as compared, for example, to the number of sensors in the array. DOA estimation methods developed under the framework of sparse representation have specific benefits. For example, they do not explicitly require prior knowledge of the number of sources. And they are known also to perform well in the case that the sample size is low, and also in the case of correlated sources. However, they also have some severe drawbacks. For example, they suffer from estimation biases. The basic idea of sparse representation techniques can be explained as follows. To avoid the difficulty of the multidimensional multimodal optimization of a non-convex manifold, AN, we can sample the field of view over a fine grid of k candidate DOAs, denoted with theta tilde. We assume that k is much larger than n and construct a fixed, overcomplete, so a fat dictionary of steering vectors over the chosen grid of candidate directions. We assume for simplicity that the true sources lie on the grid of DOAs, so on our sampling grids, hence we avoid the off-grid error problem. This assumption can be relaxed. There are many methods that are either devoted to this problem, or we also know so-called gridless sparse representation methods. Having defined the dictionary A tilde, we can rewrite our multiple measurement signal model in the following form given over here, where we introduce an extended signal waveform matrix F tilde that is in extended form of the signal waveform matrix S or of the fitting matrix F that we used before. The extension is of the kind that the matrix has an extended row dimension that matches the column dimension of the sensing matrix A tilde. For the ideal model with the true sources on the grid, the matrix F tilde is a row sparse matrix. So the rows of F tilde that correspond to the true source location contain the signal waveforms in that corresponding row, and the other rows are identical to 0. We call the matrix F tilde a row sparse matrix. Defining the rows of a k times t matrix F tilde as F1 tilde underline to Fk tilde underline, we first define the vector of row norms by stacking the individual p norms of all k rows on top of each other. For our row sparse matrix F tilde, we obtain a sparse vector as given over here. Then we can introduce the mixed norm of the matrix F tilde as a q norm of the row p norm vector. In this norm, we couple the elements in each row vector Fk tilde underbar by the LP norm. As we search for row sparse matrices F tilde, we are interested in the LP0 pseudo norm, where the 0 norm counts the number of non-zero elements in a vector. With this definition of the mixed norm, we turn our attention to the least square fitting problem introduced before, where we match our measurements x to our model. Now we use the extended model with a fixed dictionary A tilde, and we search for the best least square match of the data x with the product A tilde times F tilde. As the dictionary matrix F is a fat matrix, the dictionary matrix A is a the A tilde is a fed matrix. The matching function has infinitely many perfect matching solutions. However, we search for the minimizing solution that exhibits a row sparsity in the sense of the mixed P0 norm of exactly n. Hence a solution that has exactly n non-zero rows. In this equivalent problem formulation, we have avoided the optimization over manifold an that we used before, as now we have a fixed dictionary A tilde. However, the LP0 norm constraint is still a non-convex and combinatorial constraint. And we need to search over the set of all n row sparse matrices in practice, which is equally difficult. To solve the problem, we can use Lagrangian relaxation and write the corresponding dual function for non-negative Lagrange multiplier lambda. The Lagrange multiplier marks the cost associated with the violation of the LP0 constraint. And the Lagrangian minimization problem provides a lower bound for the optimal function value of the least square matching problem. We will later discuss practical procedures for finding a suitable choice of lambda. We first, however, remark that the relaxed problem is still non-convex due to the non-convexity of the LP0 norm involved. Hence, we want to apply approximation techniques in the following. A common convex approximation of the LP0 pseudonorm that is known to promote sparse solution is a LP1 norm. This approximation is commonly termed L1 norm relaxation, even though depending on the choice of lambda, it is not necessarily representing a relaxation of the L0 constraint least square matching problem that was given above. We speak of, formally we speak of relaxation when the lower bound property is satisfied, so when the optimal function value of the relaxed set is lower or equal to the optimal function of the original set. Here this lower bound property may not necessarily hold. With the L1 relaxation and dropping constant terms, the least square matching for fixed lambda results in a mixed LP1 norm regularized least square problem as given over here. This problem has first been studied by Malyotov, and it is commonly referred to as a multiple snapshot mixed norm regularized problem. The problem is convex even though the function is not differentiable everywhere, and it can be solved efficiently, for example, using standard convex optimization interior point solvers. If we look at the optimization problem, we note that for a large number of snapshots T or a large number of candidate directions K, the problem becomes intractable. One way to cope with this issue is to use L1 SVD. That means we take the principal T left singular vectors of T in the matching. However, this is associated with performance losses. Another way is to use a smaller grid and to apply adaptive grid refinement. Before we address the complexity issue, let us leave a few words about the choice of the regularization parameter lambda. In the choice of the regularization parameter, of the regularized least square problem, we need to find a trade-off between the data matching performance and row sparsity of the solution. We know that if we increase the value of the regularization parameter lambda, we will obtain a solution with improved sparsity, however, at the expense of matching performance. We search for a solution with exactly n non-zero rows, provided that we know the exact number of sources, which was also our assumption in the context of the other DOA estimation methods that we discussed before. In order to find a reasonable value for lambda, we can use the following useful upper bound result. It can be proven that with a choice of lambda exceeding a maximum value lambda max as given in this equation, the all-zero matrix F0 is always optimal. Hence, lambda max provides an upper bound for the choice of lambda. With this upper bound, the bisection algorithm can be used to find the smallest value of lambda n min for which an n-row sparse solution matrix is obtained. That is a solution with a row norm of f, a row norm of f being equal, or f tilde being equal to n. As we said, we can use the bisection method to find an n-row sparse solution. Then we obtain DOAs from the support of the row sparse matrix f tilde hat. That are the directions in the dictionary that correspond to the index of the non-zero rows of our estimated matrix f tilde. The situation is depicted in this diagram for a regularization parameter chosen as lambda equal to 1.82, and where we display the row norm representation versus the corresponding angle in the dictionary. However, this choice of lambda, despite the fact that it yields an n-sparse solution, may not necessarily be the preferable choice. For example, if the value of the regularization parameter lambda is large, it introduces a bias in the solution as it puts high emphasis on the sparsity regularization and less emphasis to the data-dependent matching term. And this results generally in a bias. To reduce the bias, we may want to reduce the value of the regularization term. For example, in the considered example, we reduce the value of lambda from 1.82 to a value of 0.88. In this case, the solution becomes less row sparse. We see, however, that non-zero rows around the true source rows emerge. However, in this case, instead of directly using the support, we consider the n largest maxima in the row norm representation that we see here. So we consider this as a spectrum and we search for the largest peaks of the spectrum to obtain the direction of arrival estimates. We return our attention to the complexity issue that we raised before. The problem dimension of the mixed norm regularized least square problem increases with the number of snapshots t. To reduce the complexity, the sparse row norm reconstruction, short Sparrow formulation, has been proposed. This formulation is given over here. We minimize the trace of an inverse of AG A Hermitian plus lambda identity multiplied with the sample covariance matrix R, and we add the trace of the matrix G, where the non-negative k times k diagonal matrix G is the optimization variable. We remark that this optimization problem is equivalent to the original regularized least square problem in the optimization sense. Hence, the solution of both problems are related through a one-to-one mapping. Given a solution G of the Sparrow problem, we can easily compute a corresponding solution F of the original problem through the relation that is given over here. And reversely, the value of the optimal solution on the main diagonal of G are simply the row norms of the solution matrix F for the original problem. The Sparrow reformulation exhibits some interesting properties. The dimension of the problem does not depend on the number of observations, so snapshots t. Instead of k times t complex variables in the mixed norm formulation, there are only k real-valued and non-negative variables in the Sparrow reformulation. Furthermore, the Sparrow formulation only depends on the data through the sample covariance matrix, which is a sufficient statistic for the direction estimation problem. Hence, the row sparsity pattern of the solution is entirely encoded in the finite sample covariance matrix. Only if you want to compute the optimal row sparse solution matrix F tilde, then the knowledge of the measurement matrix X is required. It can be shown that the Sparrow reformulation, despite the inverse involved in it, is a convex problem, and it can be solved efficiently for large-scale problems with a block coordinate descent implementation. For moderate dimensions, the Sparrow formulation can be reformulated as a semi-definite program. There exist two equivalent semi-definite program formulations that are preferable in different scenarios. If the number of snapshots t is exceeding the number of sensors, so that is called the oversampled case, we use the first formulation where we replace, or if you want upper bound, the inverses in the cost function by the matrix UM, and in this case we have an affine objective and additionally the upper bound constraint. Then we employ Schur's theorem to obtain a semi-definite constraint. The second formulation is preferable in the undersampled case where the number of samples is less or equal to the number of sensors m. In this case, we can replace the sample covariance matrix in the objective by the product x times x Hermitian, and use the property of the trace that we can cyclically shift the arguments in the trace of the product. Then we upper bound x Hermitian times the inverse times x to obtain an affine objective again. And then again we employ Schur's theorem to obtain a semi-definite program. Both semi-definite programs can be efficiently solved using standard interior point solvers. We study simulation results for the ESPRIT algorithm and the sparse representation algorithm. We use a sensor array of m equal to 5 sensors and sources at 90 and 100 degrees. The regularization parameter is chosen as indicated. We display the root mean square estimation performance versus the SNR. We observe that the ESPRIT algorithm shows a good root mean square error performance that is close to the Cramer-Rao bound. That is the theoretical limit of the estimation performance of an unbiased estimator, as we will see still in the following. Also, the sparse representation method works quite well. However, at around 3 dB, the bias becomes notable and we observe an increase in the root mean square error. So we have a saturation performance here. In the next figure, we study the same scenario, however, for highly correlated sources with a correlation coefficient of 0.99. Again, we display the root mean square estimation performance versus the SNR. In this case, we observe that the root mean square error performance of the ESPRIT breaks down. This is associated to numerical issues that arise when the assumption that the matrix K that we introduced that relates the steering matrix to the signal subspace eigenvectors becomes rank deficient. For the sparse representation-based methods, we observe, however, that the root mean square error estimation performance is maintained up to a value of the SNR where the bias becomes significant.